Okay, for the Unit 7 review, you can find your definitions throughout your Unit 7 note packet. For the to know part, the tenets of collision theory, there are three of them, three components of it. First of all, particles have to collide. They have to come into contact. They have to collide with enough energy that we can have bonds breaking and new bonds forming. And then they have to collide in the correct orientation. And what that means is that they have to be able to line up in a certain way, have a certain alignment to where they're going to actually have those bonds breaking and forming. Otherwise, they're just going to deflect, just bounce off one another. So those are our three tenets of collision theory. The factors that affect the rate of a chemical reaction, there are four of those. Okay. The first one is going to be temperature. If you heat up a substance, the particles are going to be moving faster. They're going to come into contact more often. More collisions means faster rate of reaction. You can also change the concentration. If you increase the concentration, you have more particles in the same amount of area, same amount of volume, and so they're going to come into contact more often. We'll have more collisions, or a faster rate of reaction. We could change the particle size, which will then impact the surface area. The smaller the particles, the more surface area is going to be exposed, more area for collisions, faster reaction. And then for the last one here, we can add a catalyst. A catalyst speeds up a chemical reaction by lowering the activation energy required to start that reaction. It makes it happen faster, and we will not actually see that catalyst as part of the products. It'll be unchanged, so we could take it back out at the end. Okay, for components of a potential energy diagram, we're going to see that down here underneath the problems. So we're going to answer that one down here. On number 4, you need to be familiar with the different temperature scales and know when water boils and freezes and know about absolute zero. So the boiling point of water in Fahrenheit is 212. In Celsius, it's 100. And then in Kelvin, when we have Celsius, to get Kelvin, remember we just add 273. So that's going to be 373 Kelvin. For the freezing point of water, it's going to be 32 degrees Fahrenheit, or 0 degrees Celsius, or 273 Kelvin. Okay, now for absolute zero, remember that's when all molecular motion stops, and the Kelvin scale is formed based off of that. So at 0 Kelvin is going to be absolute zero. And then if we subtract 273, we can go back and get degrees Celsius. And then if we converted that to Fahrenheit, it'd be approximately negative 459. Okay. To convert between Celsius and Kelvin, remember if you're starting with degrees Celsius, we're going to add 273 in order to find the Kelvin temperature. If you're starting with Kelvin, you subtract the 273 to get the degrees Celsius. And then we have Q equals MC delta T, our MCAT equation. Remember, Q is going to be the heat involved in the chemical reaction. It could be in calories or joules. And joules is our metric unit for heat. M is going to be mass, and it has to be measured in grams. C is our specific heat, and it is a value that is particular to a certain substance. It's how much heat energy is required to make a gram of that substance warm up by 1 degree Celsius. And so our units are going to look something like this. Instead of joules, you could have calories. Instead of degrees Celsius, you could have Kelvin, but it'll be one of those combined units. And then delta T is together. That's our change in temperature. And remember, the way we find that is we take our final temperature and we subtract our initial temperature, what we started with. And that'll help us determine if it's going to be positive or negative. And we'll work a problem on the next page where we'll find each one of those and plug them in. Okay, for our potential energy diagrams, if we have an endothermic reaction, endothermic heat is going into it, and it's going to feel cooler to us. When we have our potential energy diagrams, remember our potential energy is going to be found on our y-axis, And the course of the reaction is going across on the x-axis. That's just as time is passing and the reaction is taking place. And if it's endothermic or putting heat into it, our reactants are going to start out a little bit lower. They're going to have a certain amount of energy in them. And we can find that just by finding the distance between the bottom here and wherever that reactant line is. And then we start adding some energy to it. And we're adding energy up to a certain point. And then once we get to the top of that hill, our bonds have all been broken and new bonds are starting to form. And it takes energy to form those new bonds, so that's why we have a slight decrease there. And then it's going to level out. And this last flat part is the amount of energy in our products. And we could find that amount by going from the bottom here all the way up to that line. Now, at the very top here is where you're going to find your activated complex. That's going to be kind of your transition state. It's not quite products, it's not still reactants, it's kind of just in between. And the amount of energy that it took to get from the reactants all the way up to that top of that curve, that is your activation energy. That's how much energy is required to be input into it so that we can kind of kickstart the reaction, get it going. And if we look over the course of the whole reaction, our reactants started out with a certain amount of energy. Our products have a certain amount of energy here at the end. And that difference is our delta H, which is heat of reaction, which is also called enthalpy. All of these are the same thing. And since it was an increase, we're going to have a positive delta H, a positive heat of reaction. Now, if we added a catalyst to this, what a catalyst does is it lowers the amount of activation energy required. It lowers the top of that hump. Our products still have the same amount of energy at the end, but the addition of that catalyst allows those products to start forming that much quicker. Okay. So the top of that curve isn't called a catalyst, but adding a catalyst will lower your curve in the fashion that we see there. Okay. If we have an exothermic reaction, exo, our energy, our heat is exiting, and to us it's going to feel warmer because it's heating up the surroundings. We still have our potential energy over here on the side. Our exothermic reactions start out with quite a bit more energy than our endothermic reactions. We still have to add some to it. We still have some activation energy. But whenever those new bonds start to form, there's a big release of energy. So our products are down here. Our reactants are still here at the beginning. We still have our activated complex up here at the top, where some of our products are partially formed. That distance up to that point from our reactants, that is our activation energy, which we can abbreviate as EA, energy, but it's activation energy. And our reactants started out with this much energy, but at the end our products had this much. So we have a negative heat of reaction, a negative enthalpy, a negative delta H. Okay. So you should be able to look at one of these and determine if it's endothermic or exothermic just based off of whether the products have more energy, endothermic, or less energy, exothermic. And our exothermic reactions here are more likely to occur. They're more thermodynamically favored because it only takes a little bit of energy to get them started. Okay. When we have a thermochemical equation, we can identify if it's endothermic or exothermic just based off the location of our energy unit here. So we have reactants before the arrow, products after. So since our heat energy value is on the product side, that means it's leaving the reaction, it's being given off. It's exothermic, and anytime we have an exothermic reaction, the energy is leaving. So we put a negative sign in front of that value, and that's kilojoules per mole in this reaction. Again, we can split this into our reactants and products. This time our energy is going to be on the reactant side. It's being added into it. It's going to be endothermic, and that's going to be a positive enthalpy value. And it's still kilojoules per mole in this reaction. This one is one of our stoichiometry problems. How many grams of carbon dioxide, we want to find grams of carbon dioxide, are produced when 500 kilojoules of energy are used in this reaction. So we want to find grams of carbon dioxide, and we are given 500 kilojoules of energy. So we have the two parts that we can set up our mole energy ratio. Everything else we can cross out. So our mole ratio here for every 2 moles of carbon dioxide produced, we're also going to get off 1,367 kilojoules of energy. Okay. So when we write that, we are done with these numbers. We don't want to use them again. And we will always start with the number that they give us in the problem here. So we're going to start with our 500 kilojoules. And remember, we want to use our mole ratio as soon as we can. And we have kilojoules at the beginning. We have kilojoules in our mole energy ratio. So we're going to set it up with our kilojoules on bottom so that those units can cancel. And our 2 moles of carbon dioxide on top. And if we were asked for moles of carbon dioxide, we could stop there. But we want to know how many grams. So we have to find the molar mass of carbon dioxide. So we go to our periodic table, look for our table grams. So we've got carbon, which weighs 12.01, and we have 2 oxygens, which each weigh 16, and we add that together and get 44.01 grams per mole. So we already have our mole on the bottom. We'll put that many grams on top with it. So our moles of CO2 cancel, and we're left with grams of carbon dioxide, which is what we wanted in the problem. Now mathematically, remember, if it's on top here, we're going to multiply, and if it's on bottom here, we're going to divide. Multiply, divide. So in your calculator, you're going to have 500 times 2 divided by 1367 times 44.01. And we're going to get a value in our calculator of 32.194, and it keeps going. So we look at our significant figures. We've got 3 right there. We count the zeros because we have a decimal in the number. Our energy, we've got 4 of them there, and we've got 4 from our molar mass value. So our least number was the 3 of them over here. So we're going to round this to 3 places. When we look at that 9, the 9 is going to make the 1 round up. And then when we write it in scientific notation, we have 3.22 times 10 to the first grams of carbon dioxide. For our heat of reaction problem, you have to be able to look up your heat of formation values on your purple page. We need to write our formula here. The way we find our heat of reaction is to take the sum of our products, the sum of those heat of formation values, and subtract the sum of our reactants. So remember, you're always going to start with your products over here, then you'll take care of your reactants second. So let's go ahead and set up our basic formula here. We're going to start on the product side. We're going to have 2 C2H2, and we're going to add to that 5 O2s. Then we're going to subtract, and we're going to do the same thing with our reactants. We've got 4 CO2s, and we're going to add to that 2 H2Os. And then we need to look up each of those substances on our list of standard heat of formation values. And when we look up CO2, we get negative 393.5. When you look up water, you have to be careful that you're looking up the gas form, not the liquid form. You get negative 241.8. You look up C2H2, we get a positive 226.7. And oxygen is an element. Elements don't have a heat of formation value. If you look it up, it'll say 0. So we're going to plug in those numbers. We're going to have 2 times, and remember, come over here, look at C2H2. We've got 226.7 plus 5 times 0 minus 4 times negative 393.5 plus 2 times our negative 241.8. So you put each part into your calculator. We put the first set of brackets here in, and we end up with a positive 453.4. And then we do the same thing with our second bracket here, and we get negative 2057.6. And you type it exactly as it looks into your calculator. You don't have to put brackets or parentheses, but you do need to be sure you subtract the negative, and we will end up with a value then of 2,511. Now, if we look at how our values for standard heat of formation were reported, all of the ones that we have were reported out to the 10th place. And since we're adding and subtracting here, our rules tell us that we have to go to the least significant place value that was reported. So since these all reported out to the 10th place, we also need to report this to the 10th place, and it's going to be 0.0 then. And our units that go along with that, we saw it on our table that we have there. It's going to be kilojoules. We don't have to write it on every single number along the way, but we will write it on our final answer here. And if we wrote that in scientific notation, of course, that would be 2.5110 times 10 to the third kilojoules. If we look at the sign, we can determine if it's going to be endothermic or exothermic. It's positive, so that means that we have an endothermic reaction. If it was negative, that would mean that the heat was going to be released, and it would be exothermic. In endothermic reactions, since they require quite a bit of heat energy put into them, they're going to be thermodynamically unfavored. Okay. If we want to convert from kelvins to degrees Celsius, just remember your ABCs. ABC, and then goes to K. So if we're starting at K, we want to go back to C. We have to go back. We have to subtract our 273, and we're going to be left with 30 degrees Celsius. And then if we're starting with negative 75 degrees Celsius, we want to go to Kelvin. We have to go forward. We have to add our 273, and you're going to be left with 198 Kelvin. Okay. How much heat in joules, we want to find heat in joules, is required to raise the temperature of 75.0 grams of glass from 24 degrees Celsius to 575 degrees Celsius. So since we want to find heat, we're going to be using MCAT, Q equals MC delta T. So we need to know what our mass is. Our mass is going to be our 75.0 grams. Our specific heat value, C, we're going to have to look up glass in our chart of values. And since we want joules, we look in the joule column, and it's going to give us a value of 0.50. And our units that go along with that are joules per gram. And it says joules per gram Kelvin on your chart. But just remember, we can use Kelvin or degrees Celsius, whatever we need, to match the units that we have in our problem. So since our temperatures are reported in degrees Celsius, we can change that Kelvin to a degree Celsius. The difference on one temperature scale is the same as the difference on the other. And then finally, our change in temperature is going to be our final temperature, 575, minus our initial temperature. And so we get a delta T value of 551 degrees Celsius. And since all of our values here are side by side, we're just going to multiply each one of these. And when we take a look at our units, we can see that grams cancel. And this is why it's important that we put our temperatures in the same scale so that those units will cancel. We're going to be left with joules here. And whenever you multiply all of those numbers, we end up with the value of Q is 20,662.5. Now, if we look at our Sig Figs, we've got 3 of them there, 2 right here, and 3 right here. So we're going to go with our 2 Sig Figs. We look at the 2, 0, and then does the 6 make it round up? The 6 does make it round up. So we get 21,000. So we'll write 2.1 times 10 to the 4th. And our units we saw that we're left with, which is the same as what we were asked for in the problem, joules. Now, if we want to convert this into calories, you need to know that 1 calorie is equivalent to 4.18 joules. So if we take our value that we just got, we're not going to use our rounded off value. We're going to use the whole number we got in our calculator. That's how many joules we're starting with. If we want to change that into calories, we set up our equivalency statement as a conversion factor. We just have to be sure we put the joules on bottom so that those units can cancel. We're going to have our 1 calorie on top. So that'll be the unit we're left with. Remember our number down here, we have to divide by it. So we will divide and we get a value of 4,943.18. And it keeps going. So this number we started with, remember, it was really only 2 significant figures. We just didn't want to use a rounded value to do more calculations. But we're still going to go with the 2 sig figs that we know that it needs to have. And then this number down here, we've got 3. So we're going to still go with the 2 sig figs. Look to see if that 3rd digit will round it up. The 4 does not make it round up. So we end up with 4,900 or 4.9 times 10 to the 3rd calories.